Hi, and welcome to another exciting edition of math development here for 3D graphics. We're doing vectors right now, and we're getting ready to do the dot product. So let's talk about one of the reasons why we need this dot product, so you're not sitting there going, well, why am I learning this? So one of the things here, I have this checkout counter that was done in the Blender game development series. So if you want to check out how to do this, just go into and get those videos. But for right now, let's talk about how this works. So I have this counter and I have this camera, and this camera is the view frustum, right? More or less. And if it's within the view frustum or if it's within the camera, then of course it needs to be calculated in the scene. If it's not in the camera, then it's not going to be seen. See, this monkey head's outside of this view and we can't see it. So it wouldn't make any sense to calculate all kinds of models that are outside of our view. It wouldn't gain you anything. But if it's inside the view, then of course you want to calculate it. And so that's what we have to determine, a fast method in which to calculate it or not. And a quick way of doing that is to use a dot product. So if I have a vector coming straight up here from the center of the camera, and I have, and at this point here on the camera, it's 90 degrees to that vector, right? So at which point it's not with that vector at all. So unless you had like a 180 degree view, which is totally unrealistic, then you're not going to have to worry about that. Based on the view angle of the camera, so depending on what the actual radius of the degrees here for the camera, as far as that goes, for the focal length or whatever, depends on the size of the camera here. See how if I bring that up here, look what I get, it squeezes down. Now if I turn my focal length the other way, it's going to go the other way, and I'm going to get a wider and wider view. Okay, cool, fine. But again, so that's how ridiculous it would be to have it at 180 degrees. It's just everything's within view practically, as long as it's in front of the camera at that point. So I'm going to set it back to 35, and a person's going to see about 48, actually 0.5 to be accurate. Something like that right there would be what a person would see. But we're going to do 35 for now. It works for us for what we're doing. And based on the angle of this monkey head, depends on whether or not it's in the view or not. So again, we don't want to calculate it if it's not within the view. And then you get a really good idea of what I'm talking about as to why it matters. So let's have a look at some vectors, and let's have a look at some formulas. Okay, so I got two vectors graphed. I figured out how to do plotting and such in this program, and I've kind of gotten where I can get my way around, and it's quite nice. It doesn't put out stuff in a very human readable method, just kind of like a little more cryptic than Mathematica is. Maple and MATLAB really kicks out stuff in a really easy to read, pretty much the way you would write it on paper or in a book. So it's nice, but this program is more code-ish. It's more like it's done in Python, so it's really more code-ish, cryptish type stuff. So, but since you guys are all programmers, then this shouldn't be anything new as far as looking at code, and so seeing the math shouldn't be like an issue really. Okay, so I got my vectors here. In this case, I'm going to plot C and D here. So I'll plot these two vectors, and they're this much apart. I didn't want them real close together. I have one where they're real close together, and it's annoying. So I made them further apart, just so you could really tell a difference that they're far apart, and definitely not going in the same direction. I can right-click on here if I want and go in here and turn on my axes. So you can see Z is up here, Y is going into there, and X is going across. So you guys are used to seeing it this way for when you're doing the when you're graphing. You're used to seeing it like this when you're in 2D. Of course, our 0, 0, 0 world coordinate is right here at this point here, and so all our drawing graphs are coming off of there. Okay. And all I have to do is type in plot and tell it what I want to plot. And I used RGB color equals hue 2.0 in order to colorize it, based on the color, doing hue saturation value methods versus the RGB method. So, you can also explicitly use RGB method too and pass in a color vector to colorize your different things here, but I didn't do that. I just used the regular hue for the hue saturation value method instead. Okay, so cool, but need to see something more, right? Well, C dot product here is the command to do a dot product, and I said we're going to dot C with D, and then I get 23 here for my result. Cool, and this is the formula for the dot product. That whole long thing there, and it probably doesn't make a whole lot of sense. So let me switch over to a more human readable, and this is what I was talking about. It's not really all that human readable, unfortunately. It's kind of a headache. Not that one, that's the old one. This is the new one. Alright, yes. So here's our dot product. And I couldn't fit it all. Let me expand this over so we can just see it all at once. That would be nice, wouldn't it? Alright, there we go. Alright, so A dot with B, and it looks just like the multiply symbol. It's really confusing as far as that goes. I know we have our little arrows above our A and our B because they're both vectors. And then what makes it even more confusing is multiply is also a dot. So here you're doing multiplication, here you're doing a dot product, and they're completely two different mathematical operations. Cross product's not going to make it any better because later on we'll have for cross product they use an X. So it's not exactly straightforward on this stuff. And since I'm dealing with variables, I really don't want to put an X in here either because it might get a bit confusing. So yeah, you don't want to confuse people with a cross product, so I don't know what to tell you. I'm just doing smaller dots for multiply and a bigger dot for dot product. But this has always just been the way it is. I don't know. But you know, in this case, I'm going to do x from my A vector, right? So it's going to be my first value in my A, and then bx for my first value in my B vector. And I'm going to add that to my A, my second value in my A vector, which of course is y, the y value, and then my b y value, which is the second value in that vector for b. Multiply those together, and then I'm going to add it to the last value in A, which is the z, value, times the bz value, which is the last value in that vector. If you do that all together, it's going to be the exact same thing as the magnitude of A, magnitude of B, and cosine of theta. You'll get the exact same solution. And here I drew a little cosine, where we had our view frustum from earlier. I was showing you in Blender there, right, for the camera. Remember, camera. So this is the overhead view, just like we had here, right? We have our overhead view. Yes? Okay, so just like this, if you imagine this is going right through our graph right here, and then we have that sine wave coming down, right? Okay, so that gives us our angle. Well, that's exactly what's going on here. We have our camera view. If you want, I'll do this right here, just to make it more apparent. Alright, so there you see her. That's our camera from overhead, right? Just like it is here. Hopefully that makes it even easier. Alright, like that, right? Okay, so there's our camera. Exactly like that, pretty much. Alright, and so you can see if we're using our sine curve here, and it would be a smoother... I'm drawing with my mouse, so it's not that smooth. But it would be a smoother, variation across that space there, and you get a very circular-like appearance to your curve. See, right here, it's like a really clean, smooth setup. And I did an aspect ratio of 1 in order to make it nice and even and smooth like that. Okay, so when you do it right, it looks awesome. And so that's how we're basically doing our figuring out our angle here. Is it within the right direction? And if you have it as a unit vector or a normalized vector, right, the magnitude of A is going to be what? 1, right? Because why? Because remember, normalized and magnitude, you're going to divide your your magnitude by your vector in order to get it down to the 1 for its magnitude after that, which would be a normalized vector. So if these are both been normalized for these vectors, then it'll be magnitude of 1 times cosine of theta. So then you get down to this cosine of theta is equal to the dot product of A and B, a normalized A and B, in which the case this would be a little hat symbol here for the top of that vector because they're normalized. And so that's very cool, because then you could take the inverse cosine here, or arc cosine on this side to over here, and since this formula is equivalent to this formula, and if these were unit vectors, then you could take the cosine there and actually get the angle. Now, because of the way this goes, this is going to go between 0 and 1, as to whether or not it's with it or not at all. And I can show you that real quick mathematically in our Sage here. So, from a mathematical perspective, check it out. If theta is here, where are we? Oh yeah. If theta is 0 in here, if they're let's see here, where's a good example? All right, I'll tell you what, let me move my cross product up here and take my normal value, because that's completely, absolutely perpendicular to the other one here. So I'm going to bring up my cross product. We'll go over cross product here in a bit, but alright, so there's our cross product. So you can easily see that, yes, this vector is 90 degrees from both of these vectors, which is what? It's going to be D and C. Alright, so we did cross product of C and D, and we got N, which is our normal. Okay, cool. And I flipped my normal too. I'll get into that later. It's really easy. Okay, so I have my N, normal. And basically, if I were to do the dot product of my normalized N with my normalized E, or sorry, C, then I would get a result of, well, let me show you. Easier to just show you, really. Boom, 0. See, just like that, versus the 23. So, in which case, that would be 0, which is at 90 degrees. It's going to make this totally perpendicular. Why? Because this is theta over 2 versus theta down here. And remember, theta in radians is half a circle. So, theta over 2 is going to be 90 degrees at this point right here, where x is 0. And that's exactly what we got. We got 0 there, right, for our degrees. When it's completely parallel with it, directly right on top of it, then it'll be 90 degrees. It'll be 1 there. I mean, not 90 degrees, but 1. So, real quick, if I take the arc cosine of 1, and you can see the difference. We end up with 0 degrees. So there's no variation there at all. Now let's look at actually computing this correctly for what we have going on here. And there's an actual angle here. It's 9.24 degrees. So it's a very slight angle variation there. And so we get a good idea that, hey, this vector is definitely within the range of my other vector, and it's going to be drawn in the view frustum more likely than not. Not necessarily, but probably, unless your angle was so short and small on your camera there, where it doesn't encompass this. But more likely than not, with only a 9-degree variation there, it's going to encompass that model. Otherwise, you have very little getting drawn in the viewport. Okay, so that's very cool. Now let's talk about how to do a dot product. Now earlier I talked about the actual algorithm, right? Remember this? AX bx plus AY AY, BY here multiplied plus AZ, BZ multiplied all together, right? Okay, cool. That's exactly what we're doing here. So I'm doing, just to prove it, here I used a built-in dot product method function within inside of Sage, and then I'm doing it by hand the way it's actually being computed inside of this function within inside of Sage. So I'm taking the first element, which is x of C, so Cx and Dx are getting multiplied together, and then Cy and Dy are getting multiplied together, and Cz and Dz are getting multiplied together, and then they're all getting added together one by one. So the combined multiplication of these two x's here plus the combined multiplication of these two y's plus the combined multiplication of these two z's together ends up with a final result of 23. Cool. And you can even do a number verification check on that if you like. It's real simple. We just look at our values in D and C here, and again, I can prove this out further. It's not a problem. So let's just do that real quick, okay? So, I tell you what, I don't want to. I'm gonna be lazy. All right, so let me just grab those vectors real quick. Copy it. I'm just gonna move over to my terminal here and paste those in. Great. And now I'm just gonna take my C. It's a capital C there for mine, times my D 0 here, right? And I get 20. Cool. And I'm going to do my C. Well, I'm lazy. I'm not going to type all that each time. If you hit the up arrow when you're dealing with the terminal in Linux, whatever, it will pull up your previously typed commands. So this is a really quick, cool way to cycle through commands. Okay, cool. So we got 20 plus 3 plus 0 gives us what? 23, right? I'll prove it, but I mean, seriously. 23, which is the exact same thing we're getting over here in our Sage booklet. Okay, I want to get rid of the axis because I don't like it. It's just, yeah. I mean, it's cool and all, but it's just not that pretty. All right. And so there we are. We're getting 23, and you get to see exactly what's going on there. Okay, cool. And if you remember right, that's exactly what I'm doing here. And if you remember right, if I do the C dot norm open close parentheses for this, this is the magnitude of the vector. They just called it norm. I don't know. And here I normalize my D vector here and my C vector, right? So I took my D vector and then I divided it by the magnitude of my D, which is going to give me a normalized D vector. And I proved it by doing a dot norm on it, which gives me the gives me the magnitude of my normalized D vector, which comes out to 1, right? Because if it's a normalized vector, of course it's going to be 1. Remember, normalized vector is a unit vector, which means it has a length of 1. This leaves us with just the direction. That's all we want is the direction. In the case of, checking to see if something's in the viewport or not, we don't want to get a value of 23. We want to get something between 0 and 1 because then that lets us know what the angle of it is, right? So then we know if it's in the viewport or not. So we just want the direction of the vector and not the length of it too, right? Because if we have 23 in there, it's going to throw off our calculation for easily figuring out what the actual if the model is within the viewport or not, and that's not going to help us any. So this makes a lot of sense to do this. Okay. So that evaluates. We did the same thing for our C norm here, normalized C vector. It equals C divided by C dot norm, which is of course the magnitude. So our C vector divided by the magnitude of C. And now do the magnitude of the normalized C vector, and it gives me 1, just as it should. Okay. Very cool. And so then I set up some other vectors here. Well, what I did ahead of time was I just popped in there for about 30 seconds and coded out a new version of my script for generating, three sets of values that would all be perfect squares, and I did within a range of 1 to 20 for each one here, with a perfect square result, so that the numbers just play out perfectly and I don't end up with decimals. I just like having clean numbers, so it just makes it easier to do your mathematics on here, and you don't get all these weird numbers for demonstration purposes. In the field, of course, you're going to have all kinds of actual decimal numbers, but for the sake of for demonstration, it's nice to have clean numbers. Okay, so these vectors both result in clean magnitudes. So if I run these magnitudes on these vectors, I'll come out with a perfect number with no decimal on it. Great, that's what I wanted. So here I did a normalizing of the E vector here. So I did the E vector divided by the magnitude of E, and then I did the F vector here normalize by doing the F vector divided by the magnitude of the F vector. And then here I'm calculating theta. Now, you're probably going, well, wait a minute, what just happened here? Well, I just did the dot product of E and F together, right? And this has this nifty little trick here, and then I'm doing the A cosine, right? Arc cosine, inverse cosine, however you want to say it. You can say it in a bunch of different ways, but it all means the same stuff. So basically, remember, if I come in here, this formula is the same as this formula here, but I made A magnitude 1 and B magnitude 1. So 1 times 1 is what? Cosine of theta, right? So if I take the arc cosine on this side, it'll wipe out this cosine here and leave me with just theta, and I'll take the arc cosine, because whatever I do to one side of the formula, I have to do it to the other side, right? And then I have my arc cosine of this formula here, which is, my dot product. So if I take the arc cosine of a dot product, I get the angle. And that's exactly what I've done here. So, bang, I got the angle in radians. It's in radians and not in, and not in what you're thinking of for the other one. If I just do straight up, see here, let me just show you. I'll just call this dot FE or EF here, so that way we know what we're doing here. Okay. And I am going to put this dot in here within a 15 unit setup here. So instead of displaying theta right now, I'm just going to cut that. I'm going to do a dot EF so you can see what I'm talking about. And there we go. And that is the dot product of our two normalized vectors. And like I said, it'll be between 0 and 1, right? Well, since it's 1, it's really moving with the actual, it's almost in perfect alignment. And at 0, it's going to be perfectly perpendicular to it. So that's why you have a 9-degree variation here, because it's almost, perfectly within it. It's just like slightly off, something like that right there, That's about it. So you got this other vector coming off like that. Okay. So let's have our theta back again. So here's the arc cosine of it, and that's our angle there. So our angle is slight. Very slight. And basically this is a formula right here. And this is in radians after I do the arc cosine. You're probably thinking, well, I'm used to seeing it in degrees. Well, it's going to come out in radians on this. And that works out well for us, for our situation. I can convert it to degrees, but it's an unnecessary calculation when you're doing this in game development, typically. Typically, you're better off just running everything through radians, because everything pretty much gets calculated in radians and works out in radians. And then you're not converting between radians and degrees, and then back to degrees, and then from degrees to radians again, and back and forth, back and forth. It's because everything gets calculated as radians anyways. You're just going from radians to degrees and the degrees to radians, back and forth between each calculation, and it just slows things down. There's no point for doing that. So basically, if I have my degrees here, this is the formula for degrees. It's 180 divided by pi. And for radians, it's pi divided by 180. So you can see these are opposite of each other. So, if you were to multiply these together, you would get 1, So here I have theta times the degrees, and then I did a dot in on it in order to give it a digit with 15 digits for the evaluation for my decimal. And this gives me the angle of 9.24 degrees. So there we are. We now have our degrees and how much of a variation there is between them. So very cool between the two vectors. Very cool indeed. And you're probably going, well, I don't know, are those vectors really that close together? Yeah, they are. These vectors are far apart here, but I can show you two that are not, and it's real easy to do. Let me go ahead and plot these real quick. And I'm lazy, so I'm going to copy. I don't feel like making a big deal of this. But let's look at our original vectors here. And I'm going to change this to 4 and 5 for my plot points. Instead of N here, I'm going to put an E. Over here, I'm going to put an F. Now if I wanted to, mind you, and I'll just put in like a 2 here for that color. If I want to, can do a little bit more than this, really. Alright, where am I at? Oh, you know how I was talking about the sine here? I also got a little crazy with it. And here's sine taken out further, so you can see it's repeating more and more. I have an aspect ratio of 1:0 here, but I decided to also plot cosine in 3 dimensions. So I plotted about x and y, and so you can see the effect of a cosine graph in 3 dimensions. So it's kind of a little different than what you're used to seeing in like high school for just these 2D graphs. When you're doing it in like the higher mathematics here with the 3-dimensional graphing, and this one's easy for cosine anyways. It's not like crazy triple integral stuff or anything like that from calculus 3, but it basically, you can create ripples and waves. I mean, it's really cool. This is one of the awesome benefits of math. If you really get into math, it's exciting here, because I can come in here and just recalculate this as a sine here, and bam, I've changed my my graph here. And this could be like a water ripples and the waves or something like that in the water. Really easy to use that to simulate that. I'm going to go back to cosine though. Oh, and another thing I can do too, if I just change my range of my x and my y, so this is, for drawing the graph here, if you will. I don't need to multiply that times 2 here for each one of these. This is so cool. I don't know. It gets interesting when you get higher up in the mathematics. Alright, yeah, and then here we are with lots of ripples. Almost looks like crop circles. Alright, but I'll go back to the other one because it's getting a little bit ridiculous. I need to go from negative pi to pi. Hold on a second. Evaluate. And bam, there we are. So that's a little bit more, I don't know, a little bit easier to read it visually, I guess, than the other one. The other one's a little too much. Alright, so back over here. Sorry for the sudden sidestep there. And I got these plots set up here, and I just need to go ahead and show them basically. So if I go in here and put in a show, and I do a P4 plus P5, if you add these together, it lets you do multiple graphs in one basically. Now click evaluate. I still get my number here, but here I get my plotting of my 2 vectors, and you can see that they're very close together. So say this one vector here, the green one here, let's say that vector is our camera. center of our camera, and then this is the object coming off of our camera here, and it's this placement. And you can see you probably would have this fit with inside that camera range, unless your camera's really small right here, and maybe your camera's going out to here like this. Then that object would be drawn within the scene, right? Cool. I want to do a real quick show you what happens if I do this with the normalized vectors versus, because here you can see the vectors are two different lengths with this magnitude, and so we're getting direction and magnitude, and it's not really what you want per se. So if I get down to just my normalized vectors, let's see what that does for us. Okay, and now you can see more of a reason why you're going to normalize your vectors, why it's so important to know this magnitude, and why it is you need to actually go through the process of normalizing vectors. But check it out, they're the same length now. And now the only thing we're concerned about is what? You got it. Direction now. So these are both a 1 unit long vector. They are exactly the same length, and now it's just about direction. And is that model within the range of that camera or not? And is it going to be displayed? And there you go. But don't forget, dot product can be used for so many more things than just simply camera. You can use it for, oh gosh, so many calculations. Lighting for one. Just a bunch of different methods. Don't worry, you're going to see dot product quite often in the future here. You're going to be working with vectors all the time, and just about every other calculation you're doing, you're going to be using a vector. There's matrices all over the place. We'll be getting to matrices here pretty soon. Next thing up here, we're going to hit dot product, and that's really cool because basically what that allows you to do is find your normal vector. So basically I can take these two vectors here and I can create a vector that's 90 degrees perpendicular to these two vectors here, as you see here. And so if I cross this vector here with this vector here, I get a 90 degree angle vector there. And of course if you do the dot product of that we just showed you a second ago, you get 0. So we'll explain why that is here in the next video, of why if you do the dot product of a cross product vector you get 0. Of course if you're paying attention to the video you already know why in this video, but because it's at 90 degree angle, remember it's going to be 0, and I can show you mathematically why that is in the very next video. But with that, that covers vectors for dot product, why we need them. There's of course many more uses of it than what I showed you, but that's just one example of why you need them and why it's so important, and breaking it all down to all its parts and what's involved for the mathematics. But with that, very cool. My name is Nate Nestler, and this is for Hyperactive Studios. Thank you very much.